Good morning, my friends. Today is Wednesday, May the 6th, and today we will be talking about the beginning of Chapter 13, which is entitled Gravitational Interactions. So this really goes along with everything that we learned in Chapter 12, and so all of the stuff that we just finished talking about is stuff that we're going to talk about again now, this time with a little bit of arithmetic thrown in there. All right, so don't get too caught up in the math, but you'll see the algebraic and mathematical relationships that exist between the forces of gravity. Now, before we get into this, I do want to mention that there are 3 assignments for Chapter 12 that are now due or will be due by the end of the day today. All right, the worksheet 12-1, as well as the review questions for Chapter 12, numbers 1 through 10 and 11 through 14. Please make sure that you get those in ASAP, but definitely before Friday morning. On Friday morning, I would like to give you kind of a Chapter 12 review assessment during your regularly scheduled class time. So, with that said, let's move on to section 13.1, which deals with gravitational fields. So what is a gravitational field? All right, well, it's a force field, all right, and it surrounds any object that has mass. That includes things like stars and planets and moons, but it also includes things like you. You have a gravitational field, and that field is directly proportional to your mass. All right, so the more mass you have, the bigger your gravitational field will be. If you are a very large person, you have a bigger gravitational field than if you are a very small person. But even things like coffee cups and the books and whatever, the pencils have gravitational fields. Now, gravitational force is different than some of the other forces that we talk about in physics because it's what we call unidirectional. In other words, it's always attractive. Let me just give you an example. If you take 2 bar magnets, and you try to put the north and south poles together, they're attractive. Okay, but if you try to put the north pole of one and the north pole of the other together, they will repel each other. All right, and so magnetism and electric forces and nuclear forces can be both repulsive and attractive. But that's not true with gravity. Gravity is always an attractive force. In the diagram that just popped up on your screen, you can see the formula that we talked about the other day. The force of gravity is equal to Newton's universal gravitational constant times the mass of the planet or star or whatever large object we have, times the mass of whatever the little object is, you, for example. All right, so big M could be the mass of the Earth, and little m could be your mass, all right, both in kilograms. And then the value of d represents the distance between your gravitational centers. So even if you were talking about 2 very large objects, like, for example, let's say this was the Earth and this was the moon. All right, so the mass of the Earth here, the mass of the moon here, there is a force of gravity that will attract these 2 objects. Obviously, we know that because the moon is still in orbit around the Earth. And the magnitude of that, the magnitude of that force is going to be dependent upon the 3 quantities that we talked about in Chapter 12, right? The mass of the first object, all right, time, and the mass of the second object divided by the distance between them squared, right? That's where the inverse square law comes in, all right? So we have to keep track of these numbers. Let's go back. G, which is Newton's universal gravitational constant, so it's a constant number, mass of the bigger object, mass of the littler object, distance between their centers of gravity squared. Okay? Okay. So how do we actually approach this? Well, if you recall from way back when, we know that any force is equal, according to Newton's second law, as F equals m times a. Now, if you're talking about the force of gravity, then the force of gravity is going to equal mass times the acceleration of gravity, right? And if I rearrange that formula algebraically, I come up with this, all right? The acceleration of gravity is the force divided by the mass of whatever object you're talking about, okay? Now, if you recall from chapter 12, we have the force of gravity is equal to Newton's universal gravitational constant times the mass of the object times the mass of the planet, we'll call it planet Earth just here, divided by the radius of the Earth squared. All right, this is Newton's law of universal gravitation. Now, here's the tricky part. This is this. Okay, so what I did here was I replaced force with G times M over R squared. But it's still divided by this little m. And so now what I can do is I can cancel out the masses. And so what this implies is that your mass is irrelevant. Okay? A big person and a little person will experience the same acceleration of gravity. Okay? Little g, because there's no your mass is irrelevant here. It cancels out in this particular equation. So now, if we look at the numbers that are left, I can calculate the acceleration of gravity on any planet if I know Newton's universal gravitational constant, which is this number here, that's big G, the mass of the planet, which for Earth, this is Earth, the mass of the Earth we know is 5.98 times 10 to the 24th kilograms. That's a lot of kilograms, all right? And divided by the radius of the Earth squared. And the radius of the Earth is 6.37 times 10 to the 6th meters, okay? So that's a lot of numbers. So, whoops, go back. So now I'm going to take this formula and bring it up here and do some plugging and chugging. I got 6.67 times 10 to the negative 11th. I'm not going to write out all the units. Times 5.98 times 10 to the 24th kilograms, all divided by 6.37 times 10 to the 6th meters quantity squared. Now, if you take a minute here and plug all these numbers into your calculator, 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th divided by 6.37 times 10 to the 6th squared, guess what you get? This equals 9.8-ish. All right, rounded, of course, but meters per second squared. All right, I plugged in the mass of the Earth, the radius of the Earth, and that is the acceleration of gravity. And so that's why every object on Earth, whether it's a person, a baseball, a pencil, a coffee cup, all accelerate toward the ground with the same acceleration, 9.8 meters per second squared. Okay. So that brings us to example number 1. All right, and the question is, why do all freely falling objects have the same acceleration? Okay, well, if you think about that, we just answered this question, okay, because the mass of the object itself is irrelevant compared to the mass of the Earth and the radius of the Earth. And so right here, the masses of the object, you or a coffee cup or a baseball, they cancel out. And so the acceleration of gravity is due to three constant numbers: Newton's universal gravitational constant, the mass of the Earth, and the radius of the Earth. And so that's why all freely falling objects have the same acceleration on Earth. Okay. Now they'll have a different acceleration on the moon, on Mars, on whatever your home planet happens to be, right? But on any of those planets or stars or moons, the acceleration of gravity will be the same. All right. So when we studied Newton's second law in chapter 5, we learned that acceleration is equal to force divided by mass. In free fall, that ratio, F over m, is the same for all masses. So the acceleration has to be the same. In this chapter, we're saying the same thing from a different point of view. The concept of the gravitational field, little g, also equals force divided by mass. And so from Newton's equation for the force of gravity, we see that F over m at the Earth's surface always equals 9.8 meters per second squared. Now we've been using 10, and we can still use 10 meters per second squared as our gravitational acceleration. But in the same gravitational field, g, little g, all freely falling objects have that same gravitational acceleration, about 10 meters per second squared. Okay. Now, example number 2 says, the acceleration of objects on the surface of the moon is only 1/6 of 9.8 meters per second squared. So, in other words, the acceleration of gravity on the moon is less than the acceleration of gravity on Earth. Okay. From this fact, is it correct to say that the mass of the moon is therefore only 1/6 the mass of the Earth? Any ideas? Well, again, let's get rid of that. Let's say that G equals G times big M, the mass of the moon or Earth, divided by R squared. And so would it be right to say that the mass of the moon is only 1/6 the mass of the Earth? Well, that is not really, it's not, okay, it's not true. Because even though G is constant no matter where you go in the universe, the mass of the planet you're standing on differs, but so does the radius of that planet. And so the answer to this question is no, it's not correct to say that the mass of the moon is 1/6 the mass of the Earth, because you have to take the radius of the moon into account as well. So the answer is no. We could conclude that the mass of the moon is 1/6 that of the Earth only if both the moon and the Earth have the same radius. Okay, but they don't. We know they don't. And so the radius of the moon is only 1.74 times 10 to the 6th meter. So it's considerably smaller than the radius of the Earth. And so it's in fact less than 1/3 of the Earth's radius. And its mass is 7.36 times 10 to the 22nd kilograms. And so that's about 1/80th of the mass of the Earth. All right. And so the answer here is no, it does not work out that way. Another way to look at this kind of thing, looking at and using the formula that we've got written here, is shown in example 3. How does the acceleration of gravity at the surface of Jupiter compare with the acceleration of gravity at the surface of the Earth? Jupiter's mass is about 300 times that of Earth, and its radius is about 10 times greater than the radius of Earth. So if G for the Earth is equal to big G times the mass of the Earth divided by the radius of the Earth squared, and the acceleration of gravity on Jupiter is equal to, again, big G, same number, times the mass of Jupiter divided by the radius of Jupiter squared, then we could say that this is big G times, now watch this, all right? We said that the mass of Jupiter is 300 times the mass of Earth. So rather than m sub j, I'm going to write 300 times m sub e. And I'm going to divide that by, rather than using the radius of Jupiter, I'm going to use 10 times the radius of Earth squared. Now, that's going to give me 300. I'm going to use the commutative property of multiplication here and move this out. 300 times g times the mass of the Earth divided by, now watch this carefully, what is 10 RE times 10 RE? It's actually 100 RE squared. Now, 300, this is going to be the gravity of Jupiter. 300 divided by 100 is, of course, 3. And this, g times me times m re, I'm sorry, g times me over re squared is equal to simply g e. And so the answer here is that the acceleration of gravity on Jupiter is about 3 times greater than the acceleration of gravity on Earth. All right. Now, I know that's a lot of math, but notice I didn't have to plug in any of those big ugly numbers written in scientific notation, right? The 6.67 times 10 to the negative 11th and the mass of the Earth and the radius of the Earth. I didn't have to use those numbers because algebraically I ended up canceling this out to make it g sub e. All right. So in the end, the answer here is that the acceleration of gravity is equal to 3 times on Jupiter is equal to 3 times the acceleration of gravity on Earth. So Jupiter's acceleration of gravity is around 30 meters per second squared. Okay, so that ends our discussion here of section 13.1. Again, please make sure that you finish the assignments that are due for chapter 12, and we'll talk about a review assessment for chapter 12 on Friday morning. All right, have a great day, guys. Am I still recording?